Bonjour à tous. Hello, everyone. I'm going to go into English because I don't speak French that well, but welcome, everyone, to this is our lightning talk that we're going to have with a very, very special guest today. I'm going to start by saying thank you to everyone that is in this lightning talk. We know that there are people that are going to start coming into the webinar, so feel free to jump into the conversation in the chat. If you have any questions about our presentation today, please put them in the Q&A. And as a reminder to everyone that has been part of this series or those who haven't, we are recording these sessions. It will be uploaded into the forclimate.ai website. And we're very excited about this one. So to introduce myself, my name is Lucia. I'm the director of the Global 2020 AI for Climate Forum. And to give you a little bit of context about AI for Climate, is an initiative that was launched in February, and it aims to harness the power of artificial intelligence to tackle the fight against climate change. What we want to do is understand how this exponential technology can actually help in the powers and in the fight against climate change. And this year we're focusing on conservation a lot. So we're gonna have our first forum on the 25th and 26th of November online. And so we welcome everyone to register as well on that same website. And without further ado, I would like to say that we came across Tom Landry, who is our speaker today, and the Senior Advisor of Partnership and Business Development at CRIM, because we at CMinds, at AI for Climate as an initiative, have a very special relationship with the delegation of Quebec in Mexico. And we asked, like, hey, do you know anyone that is doing work that crosses between AI and conservation and climate change and climate tech? And they said, oh my God, yes, in Canada and in Quebec specifically, we know a couple of people that are doing this. So we're very glad that we were introduced to Tom. So thank you so much to the delegation of Quebec in Mexico. And I am not gonna do any more introduction. I'm gonna give the microphone to Tom so he can start his talk. So Tom, welcome. And let's start with the topic of the use of technology to understand the effects of climate change.
Merci beaucoup pour l'introduction. Thank you very much for the intro. So I'm Tom Landry. I work at CRIM, which is the Computer Research Institute of Montreal. I'm a senior advisor there. I'm a specialist in different things at CRIM, mostly in geospatial information. So science of where, what's happening where. I've been at CRIM for the last 15 years or so, and we've been doing quite a lot of projects in that period. But lately, in the last 5, 6, or 7 years, we've been more active in climate services. So part of what you'll see here is the result of our various projects. So the type of discussion I'd like to have with you today, so I'll present just a bit of what is CRIM. I'll try to give you a primer of how to understand climate change. I'm not a scientist. I'm not trained into the specific science. I'm more a computer engineer. But how do I understand climate change? How do my team build a tool to help people to understand climate change? I have a main topic for you as an example, hydrological modeling. So part of the discussion will focus on that. And then what does it take to support all of this, to make that happen? What are the technologies we're talking about? And then I'll try to leave you on the inspirational note of what can come next. So CRIM is an applied research center in Montreal. We've been working for quite a while now, funded in 1995. We're non-for-profit. And we're financed by the Economy and Innovation Ministry of Quebec. I think they are online, so thank you for your funding. It's appreciated and necessary. CRIM's mission is a dual mission of economic development and technological transfer. So we try to get ahead of the wave and so we can better serve the different organizations in Quebec. and give them a head start. And we also produce new knowledge. We also do research that we can transfer from academia to industry. This picture gives you an idea of where is our mean of intervention, where we do the innovation, pretty much at the dead center of the research aspect and applied development. So on the left, you would see what universities would do, fundamental research. That's not exactly what we do. And on the right-hand side, private companies that might do R&D in-house. We're not a development company, no, either. So we're really in the middle of both, trying to speak both languages of academia and enterprise. So I'm now jumping in the topic of the talk is understanding climate change. So what do we need to understand climate change? We need to talk about physics and mathematics and different systems. So I'll do that by introducing some variables. I'll talk about the dynamics systems, how it progressed through time, and what type of model exists at the global scale. I'll introduce you also to different sustainable development goals to try to narrow down the fields of intervention we have. And I'll present some projects we have at CRIM that are in line with those SDGs, so animal migration, land and forest, and coast and water. So to understand the climate itself, we need to measure it. We need at some point to get a measure of the real world so we can know how it will evolve or how it was in the past. So this is from the pretty large undertaking of knowing it's the Global Climate Observing System that structured that discussion. So at CRIM, we work a lot with remote sensing, with information from satellite. So from that, we could study lakes, where you see here lakes and sea ice. This is something quite important in Canada. And on the right-hand side, everything that is above ground, which is the biomass, the forest, the agriculture part, and also at the complete bottom right, rivers discharge and water use. So really all of this is important to understand climate change, to see how it was in the past, how it will evolve. But my discussion will speak mostly about lakes and forests, I guess. So those variables being temperature on the ground or wind speed or everything that you might know that is a variable in those systems, they vary through time. So when you observe, you build an history of things in the past, which you can use to predict the future. So once you have that knowledge, you can extrapolate what will be going on. At that point, you probably already use a model or a formula that helps you say, this is the past, now tell me what will happen in the future. In the short term, we call that forecast. For instance, meteorological data. What temperature will it be tomorrow or in 5 days? It's pretty much short term, and it's something that is still hard to do. Pretty down the line, the further you go in the time axis, the more we start to call that projections. So I have a few examples for that. For instance, at the present instance, if you're in a city, you have probably sensors everywhere that can measure water levels or water pressure or everything that is related to the different systems. This is the present. You want to use some type of forecast to say, will I be in trouble? Is there any storm surge alert or flash flood alerts that might raise those levels, so I'm in trouble? This is still short term. In the future, in the longer term, you would say, I'm about to build a water reservoir. I'd like it to stay for 100 years. What type of precipitation can I expect in 50 years from now? So it's pretty much different. You would expect it to be pretty much different system that give you that information. Climate models, a lot of local, but the effort is most of the time or very often global. So we have several institutions throughout the world that are studying mostly the atmosphere, and they take it piecewise by small grid elements. So they can finely tune those small parts over their land, and they can simulate what will be going on or predict what will be going on there. As technology evolves, those grid elements, those cells are getting smaller and smaller as the resolution increases. So a lot more data is coming in. So for each of those cells, one of the challenges is to take in account all of different models. For instance, here, the ecosystems on the ground. What is living there? What are the forests? What type of birds or mammals are living on the land? How is the land evolving? Is it degrading? Is it desertification, or is it lush forest? So what is the land use and the land cover of those places? It's important to know how it evolved and how it will evolve in the future. And the water cycle is something also pretty interesting. So to know water evaporation, formation of clouds, and then precipitation, and all those systems are linked together and form something that we can call a climate model. I think most of you might know this by now, the framework of the UN for Sustainable Development Goals. So this is a way to say how are we doing for managing the Earth, the system, and the quality of life of its inhabitants. So these development goal at CRIM, some of the applications we do are managed for clean water and sanitation, life on land, life below water, and sustainable cities. So most of the projects I'll present to you are linked to those topics. How will that environment change? How is it right now? How will it change, and what impact will it have on water access, on the life itself, and on the cities you're living in? So straight into the projects now. First project I have to present is basically two different projects, but just to tell you that through remote sensing to satellite information, we can quickly, for large regions, classify the land and know what type of marsh or trees we're looking at, or is it dry land or very humid land. So this is the right-hand side. And on the bottom left, what you see is we can do at a much finer scale and try to see what type of trees am I looking at. Individual trees, is it a spruce or a pine or whatever. So this takes quite a lot of technology, in some cases AI, we give examples and we train a system to be able to classify and recognize things. Second project is on biology. So a master student came from Liège University with collaboration at University Sherbrooke and CRIM, and we helped him develop a system that can detect, so knowing there is animals on the ground, and recognize those animals. Is it a buffalo or any type of other animal? This is also typical steps into AI systems of detecting, localizing, and tracking animals. So for instance, for conservation, you would like to know where they are coming from and where they are migrating to, and for poaching, fighting poaching, for instance. Third project is on coastal batimetry. So what you see on the left-hand side is actual measurement of the elevation of water. So we take sensor gauge and we say this is a 30-meter under the sea. And from those information, we train an observation system to say, when you see that type of color in the image, this means you're at 30 meters or 50 meters or so on. So we use remote sensing to extrapolate the batimetry, which is basically the elevation underneath, the elevation of the seafloor. The link to that is that we had several other projects at CRIM with water management, lake extent, and so on. But that leads me to the introduction of the topic of hydro modeling. So this is a complex system. Everything that is water related, as I said, this is a system, closed loop, formation of cloud, and so on. But I will present to you some more specific. So what are the application of hydrological modeling? What is it used for? And what type of project do we do at CRIM that supports that effort? So on this application, why would you like to do models of water, of the water, natural water or fresh water, or even coastal or ocean? You want to do that to evaluate the flood risk. Sometimes it's for energy. So in Quebec, we have a lot of hydroelectrics, hydro power. So potential of those power in the future and in the present. Water allocation for agriculture, for the people living on the land. How do you allocate that? To design infrastructure, to have engineering tolerances for buildings, to be able to support storm surge and so on. and fish habitat. So if there is risk of contamination of water and so on, to see how the fish population might migrate. So into projects, into the modeling. So on the left, you know the climate modeling, we've introduced that. What is the temperature and precipitation pattern on the Earth at fine scale? We want to use that and feed that into hydrological models. So the watershed aspect, how will water flow from one place to the other? What happens if we have more water? How it will flood the plains and so on. And from there, we'd like to move to hydraulics. So looking at rivers, what is the flow of those rivers? What type of pressure can we expect? This is really an engineering problem when you're at the right-hand side. So really the variables here is what we like to get at is if we change the model, what type of flow can you expect from a river and what are the impact on flooding or on your hydro production, for instance. So you can see here different experts and organizations that work on such projects. I already spoke about batimetry, the elevation under the seafloor or of the seafloor. We do the same, and the same is important also for what's on the ground. So in Canada, we're quite lucky. There is a very nice coverage of high resolution LiDAR, so 3D sensing of the ground, elevation models. And from that raw data, which is I think 1 meter resolution, which is quite good for that extent, at CRIM we can develop deep learning techniques to be able to rapidly segment that and know these are cars, these are trees, these are roads, and from that we can rapidly know what we're looking at and what could be the impact of potential flooding or landslides, or if the land change, what is impacted. Again, this is project we've done with partners at Natural Resources Canada and Open Geospatial Consortium. If you remember, a very important aspect is the climate data itself. So in Canada, we're also lucky for that. There is a pretty nice consultation on how to manage climate data, climate projection. So we can get that at a pretty fine scale. We have a downscaling of that, meaning that we can have global climate at about 10 kilometer resolution. We also have averages. We can average that in different regions. So for instance, on the right-hand side, you see for the region of Saguenay in Quebec, which is about 99,000 square kilometers, pretty much like the Jalisco region in Mexico. We can have an idea of what will be the maximum temperature in the future under different climate scenarios. We also have at our disposal the history. So in June, habitually, what type of weather can we expect from an observing period of 1981 to 2010? So a lot of people are working on this right now from different provinces and different angles also. So now that I've presented to you pieces of what we need to understand climate change, basically, everyone knows a bit about climate change, about its impact, about how climate is changing, about how to adapt. So knowledge is shared throughout all these projects. But one thing is for sure, we always need technologies to enable that. We need computer, we need data, and we need process. So for that section, I'll introduce you to the problem of scale. You always have big data or smaller data. So scale is one important thing to consider. And again, I'll talk about two projects we have at CRIM that are, say, federating projects that are supposed to tie that all together. So what is our problem with scale is that, again, you have a variable. Depending on who you are, what you manage, or what is your region of interest, you have different type of data. You have different amount of data, different ways to sense that data. So locally, for the example I have to you have a bunch of thermometers on the ground station data, or you have weather pressure gauge. This is really local. This is a point on the map. Moving up, you have the region of interest. Is it your community, your city, your region, your county? So it's getting larger and larger in space, and the volume most of the time is getting higher. You have, of course, national scale. So I presented to you one of the example, climatedata.ca. Before going there, we could have, let's say, a continental scale. And from the global scale, the major initiative to manage all the global climate model is the CMIP project. So again, I invite you to look at the CMIP project. institutions from all over the world sharing their view of how the climate will evolve, taking all of that into account, and you have a single source where to get that information. Problem we have with this is that depending on where you start from, you need to get more information. For instance, if you take thermometers, you might have a few stations here and there. You want to know, extrapolate what the temperature will look everywhere on your region. This is upscaling. The inverse is also true. If you take global data and you want to know in your city or in your very small patch of land, how will climate evolve or what the meteo forecast will introduce to you, you need to downscale. You need to apply some statistics to a global model and fit it onto the topography, for instance, of your terrain or different systems. So you always need to go from one side to the other to have a broad view of that. This is an interesting data set to me, and it's, I think, of interest also to you, is that there is coordination in North America to manage, in that case, watersheds or land cover. This is the Commission for Environmental Cooperation that is managing all of that. I think that's a very interesting view of what is North America. We see frontiers all the time, but there is a natural boundary, which are watershed, the way water flows from one part to the other. So you can see that Quebec is joined almost to Mexico or to the Atlantic Ocean. The same is true for the Pacific Ocean. So we're linked to natural formations, and this is the type of management that can be done at watershed level. Now I'm really close to technologies and innovation. So we're working with several organizations to build modern infrastructure, modern architecture, so we can connect it together, get that data, process it, and provide some output to other people. So one thing that is getting clear is that I only have like 50 seconds. So Lucia, I'm concluding. The old model doesn't work anymore. There is too much data. You cannot necessarily expect people to come in, find your data, download it locally, terabytes or petabytes of data, and do the processing. So the paradigm needs to change. So this type of work at the OGC, led by European Space Agency, is we try to get the application, get the process or the model to the data. So it's much smaller and much more efficient. So this is a pretty big change for the industry and to the standards that will evolve. We try to do the same at the national and even international level with some funding from the Canada Foundation for Innovation, CFI. We try to get a cyber infrastructure rolling. So we build a cyber infrastructure, web services, and data lakes and data warehouse and processing that can link Earth observation, so what we observe on Earth right now, and climate projection, bringing that together in a uniform environment, AI-enabled environment, because a lot of this application, this is an AI-based application. You provide a lot of examples, you train, you get that as an application, and you process it. So this is a pretty big undertaking, and we're doing that again on the collaborative partnership with different provinces, but also with abroad with the Earth System Grid Federation, for instance, to connect to the global repository of climate information. So this is an ongoing project. This is one of our biggest and most important projects. This is not the only one, but as you can see, this is where technology needs to evolve, to get to modernize, and to get integrated and shared with people. So we're working in an open science, open innovation, and open source fashion. So I'm at the end of my talk. So what's coming next? What we see and what I hear is that people are working very hard to have a digital twin of the Earth, a representation of the state, the current state of the planet Earth, and some way of querying that Earth. How do you feel, and how will you feel in 10, 100 years or so? And how well are we doing into making it better? Maybe it's too ambitious. Maybe we should start with a digital twin of North America. It would be much simpler, of course. So looking at the different ways it can happen. So as you might know, the Ministry of International Relations put us in touch at CRIM with CMINDS, but I know about different ways that can work, but if you're listening from province of Quebec, the government of Quebec is offering some financing, finance opportunities, so to build collaborative project with Mexico and Quebec. So basically a lot of things it can happen, but as you can see, it takes quite a village to build a digital twin of the Earth. So that's it. I yield my time for questions.
Thank you so much, Tom. And yes, as he said, we're all available to talk about more on how we can collaborate with you if you're listening. And we do have a couple of questions from the audience. The first one is, what is the resolution to identify mammal species from, I don't know, from the...
Yeah. Good question. So we work mostly with optical imagery, very high resolution imagery. So we can expect something like 30 centimeters to 50 centimeters per pixel. Higher than that, basically, you know, there is a moving pixel, but you cannot recognize what it is. So you take very high resolution imagery. Problem with that is that very high resolution imagery, you cannot cover very, very large. So you have to know where to look, basically.
Yeah, exactly, because you need more space to store those images, right?
That's right. It's about space, but it's about the satellite. When it comes, the path of the satellite is narrower than large band. That is, for instance, the radar information is much larger. The resolution is more like 100 meters, 50 meters, depending. But yes, 30 to 50 centimeters, sometimes a meter resolution, but that's a meter resolution it's not that good.
Okay. And then another question is, in the case of Latin America, that we have probably a weaker technology infrastructure, how can we bring more projects like this that use the data that we have? So as you, I don't know if you know this, but in Latin America, we're starting to get more involved into AI. We're starting to collect more data, but not as it has been collected in Canada or the US or maybe some European countries. So what would you recommend to Regina in this case?
I'm not sure, 100% sure, but I'll put that map so we can think about it. So there is already work of management of that data at the North American scale. So this could be a starting point, maybe more on the policy aspect or at key data. But at some point, you'll need an infrastructure to manage that. You need places to store that data or to pull it from. So integration and interoperability of the data will be key. Sometimes you will not be able to produce that data, and that is fine. Climate models, they're already produced, and you can rely on even international infrastructure to take climate information and downscale it to the region you're looking for. So again, upscaling and downscaling. Upscaling, what do you measure in your cities? Do you have sensors? Do you have cameras? Do you have clearly satellites are looking at your regions. So it's always depend on where you're starting from. It can be punctual observation. I think in that large region, there is a place where we should look more closely because of the vulnerability of the biology or whatever the reason. So identification of the places that are sensitive and that should be observed is also important. So where do you starting from? It depends on what is your concern, I guess.
Okay, thank you so much. And then Manuel says, merci pour la présentation. Two questions.
Mon plaisir.
Two questions. One, data is fundamental. How fast is it collected, processed, and shared? And if you want, you can start with that one, and then I'll ask the second one.
Okay, so how fast? It's getting faster and faster. Problem is that a bit like what is done at NASA and European Space Agency, there is an exponential abundance of sensor of satellites. So it's getting faster and faster. So it's a big data all over again. It's too fast. Basically, you have too much information and you need, the name of the game is data reduction. You need less. There is too much, you need less. You need something to be able to, downscaling is an interesting part. Take that data that is daily, you have data that is coming at every second, every minute. You have too much. Downscaling or data reduction is very, very important. So you just take what is absolutely needed at the right time. and that will get worse. That's why the old model doesn't work. You cannot expect people to download every day the new data that came in. They say people will put an order. They say, when you have new data, don't send it all to me. Just send me that signal. Just send me that detection of change of the land, whatever it is. So that's why you need to put that application. You need to say, this is what I want to be notified of. And this, if we can achieve that, then you get the data you need at the right time.
Perfect. And then the second question is, modeling is key to get top line understanding, but moving backwards from global to local view or analysis, what that could make analysis and solutions more difficult. Is there any action to reduce the situation?
The downscaling is something that is not easy. It's a statistical process for climate. If we're speaking mostly for climate and even for meteo, we're working also at CRIM with AI to have a hyper-regional downscaling of forecasts. So this is still an active research topic, but it can be as simple as getting averages. I showed that some of the images to you here. If for you, at your level of decision, it's fine to know that your region, on average, will get 10% more precipitation in the future. This is relatively easy. This is a GIS operation of averaging all the observation. So some things are easy, some aren't. So I'm not sure I answered the question, but there is always a solution to actually give that data. What is difficult to me to understand is, even if I give you those averages, what can you do with them? How does that feed into your model, into your concern? And this is one of the concerns. For instance, I can point to you to very high resolution climate information for your region, but how will your scientists use that to predict the future? This is where science is it's difficult. It's a complex problem, of course.
Thank you so much. And then the last questions we have so far is, what is your position about having open data platforms that allow citizens to get involved in projects such as the ones you mentioned?
A very good question. So it depends a bit on where you come from. Again, where is the funding coming from? At CRIM, we're at first, but not now, but at first we try to at least give the scientists the tool they need, so they don't spend that much time to process data. So feeding the needs of scientists is one. This is what we will do with Canadian Climate Services. We work with scientists. We want to automate or accelerate their research so they get better access to data. For the other project is here, climatedata.ca. What we try to have is to provide decision maker with that data. So it's simplified, it's averages, it's something that we explain also in context. So it depends. Do you take decision? If you do, maybe this is more the level of data portals than instead of data platform. If you work with a platform, you expect more web services and stuff like that. In the portal, it's a more knowledge way, more here is how to interpret this, here is the type of decision you should take. For a citizen itself, so not necessarily in the decision process, an involved citizen, it's more at citizen data level. Some municipalities or some cities offer that. The city of Montreal have citizen initiative, but to link that through citizen to decision maker to scientists, again, sometimes you take different platform or portals.
Yeah, that's totally true. And then I have one last question for you, and it's, how would you feel about, well, how do you feel about what people are doing? Like, I know that there's a lot of efforts going on, and I know that from the AI for Climate initiative, we have found like so many great profiles such as yours. But how do you feel when people like really don't understand how can we that we're kind of understanding a little bit more about this, the imperativeness that is climate change, and how scientists are trying to tackle and trying to connect and trying to predict what is going to happen in the next 5 to 10 years, which seems pretty important. What would you say to people in terms of how to educate themselves to understand a little bit more about how they can, first of all, if they be involved, get involved, and second of all, like understand the technology behind and how that technology is helping solve all of these issues?
Once again, it depends on who you are. But if I speak about scientists, it's easy to assume that they are always on top of things and they know everything about the new technology, but that is not the case. For instance, for remote sensing, the field is transforming quite fast. Before it was very statistics based and heuristics based. Now, machine learning, everyone is looking and say, oh my God, it's changing the way I'm working. It can automate or improve or accelerate what I'm doing, or it can make me obsolete. Not necessarily, I'm exaggerating. Of course, I always need people, but we are reviewing a new starting line for several of key fields of study. So it's normal to be intimidated and say, oh my God, it's AI, it's so complex. Some things are simple or under control, like detecting stuff or recognizing stuff. It's been a while now in the computer vision community that it's doing great. You know that it's a cat or it's a car. This is pretty much solved. What is not solved, what is very complex, at least to me, is what will AI, what is the really, imagining like you can ask a robot, what is the future getting to us? And having some intelligence that can provide you with answer or say, look at this, this is important, or I need more information on this, or the AI component, not necessarily the machine learning aspect. This is a different discussion. This is also about the language. How do you ask that question to the system? And how do you get that answer? So there is linguistics and natural language processing aspect leading to AI. This is, to me, a bigger challenge. And going back to how can you learn more about this? Well, variables. What are the variables? What do you have a hold on? What do you observe on the ground? What do you know about the knowledge, the human knowledge? This is something that is already a good starting point. Where do you live? How was it before? Where is it going?
Amazing. Well, thank you so much, Tom. Louis says, merci beaucoup pour cette merveilleuse présentation, Tom. Oh, Jesus.
Merci.
My French is very rusty, but I try. So thank you, Tom, again, for your time for this presentation. For everybody who attended, thank you so much. And again, we leave you with the invitation to attend our Global AI for Climate Forum that is going to happen on the 25th and 26th of November. Via Zoom. It's a limited amount of seats, so we recommend that you register as soon as possible in the website. And yeah, thank you so much, Tom, and the CRIM team and the delegation of Quebec in Mexico. And we will see you next time.
Bye, everyone. Take care.